Alright, so I've recorded this video twice and my microphone didn't work on either. I've tested it now, it seems to be working, so this might not be my most enthusiastic video, but we're gonna get through it. Maybe that'll cut down on some of the rambles and side conversations I have with myself. So this is gravitational, potential energy, and kinetic energy. We're going to do a few days on energy. It's a pretty straightforward topic, not too much math. There's a couple tricky parts that I'll go over in this video, and then we'll end with torque, because I know you guys were very interested in torque. So let's just get right to it. So I did not make these notes from scratch. Of course, I added and changed things, but I actually got the basic version from one of my former coworkers, and he always liked to start with these objectives, and I probably should too. But our goals, you can see, are very calculation-based. We're going to calculate energy in its gravitational potential form and its kinetic form. So let's start with this thought experiment. We've got cart A, cart B. They both have the same mass, and they're both at the same height. And we let them roll down those two ramps. Cart A has a long, shallow ramp, and cart B has a shorter, steeper ramp. Which one is going to be faster when it hits the ground, or are they going to be the same? So think about that for a little while, and then I'll reveal the answer here in about 10 seconds. So here's the answer, the same, and we're assuming no friction. So friction actually would potentially change these scenarios or any real world thing like that, but not significantly. Honestly, it would take a pretty long ramp before you start seeing any significant change in speed at the bottom because of friction stealing our energy away. So however, if there's no friction, then we can say with pretty much absolute certainty that these two objects would have the same speed when they hit the bottom. They performed a similar experiment on the moon. There's no air resistance on the moon, and so astronaut dropped a heavier object and a feather. I don't remember exactly what the object was, unfortunately. I'll find a video and I'll add it to my YouTube channel to show you, but essentially we did get to test it with no air, and both objects fell at the exact same rate and landed with the exact same speed because they started with that same height, that same position in the gravitational field. So let's continue on. So let's look at the words themselves. This word potential you may have heard before, and kinetic probably not heard before unless you've been exposed to physics, but maybe you've heard words that sound like it. So potential is a word that means like has the ability to do something but maybe isn't doing it quite yet. So an athlete, like a rookie who has a lot of potential, is maybe not the best player on the team yet, but in a few years maybe they will be. They could be really, really good, but maybe they aren't yet. So potential energy is energy that's not moving anything quite yet, but it could move something, such as gravity, right? This cart here, maybe it's got the brakes on, so it's not moving, but it could move. Gravity is giving it that potential to move. Same thing, kinetic energy, kina, this root word here, like our kinematic equations, the big three motion equations, means motion. Kinetic energy is literally energy of motion, movement. So once something is moving, it has kinetic energy. Gravity deals with position, so the higher up something goes, the more potential energy it has, right? If you drop a penny on the street, it'll fall about 5 feet, right? When you drop it from your average, where your hand is. If you take that same penny up to the top of the Empire State Building and drop it, it will have a lot more potential energy because it started a lot higher up. Gravity has a lot more room to accelerate it, to increase its kinetic energy. And then as it falls, it gets more and more kinetic energy as it speeds up faster and faster. So kinetic energy deals with motion, potential energy deals with position. And there are other types of potential energy as well. In this class, we're just going to talk about gravity, but there's chemical potential energy in like batteries or your cells. things like that use chemical reactions to power motion. Gasoline in a car is a chemical potential energy, right? Gravity isn't what usually powers our car. It has a different form of potential energy in the gasoline, and then we burn it and get that kinetic energy out of it through a series of mechanical devices and stuff like that. So there's not just gravity. That's the one we're going to focus on in this class and do all the net math with, but there's many forms of potential energy as well as kinetic. The most basic form of kinetic energy is just like this, where you have some object moving. But there's heat, which is just random motion of atoms and molecules and particles like that. There is sound waves, light, electricity, anytime something's moving, right? So in electricity, you have the electrons moving through the wires. That's kinetic energy. Sound waves move through the air. That's kinetic energy. Light goes from the sun to the surface of the earth, or from your light bulb to your face. You know, whatever it is, that's energy being carried through motion. And you know it's energy, right? You stand in the sun, you feel the warmth of the sun. That's energy being carried through space by a wave. So that's kinetic energy. We're going to focus on the two basic kinds, gravity as a potential energy source and just the basic motion of objects. So, anything that's in a gravitational field has some sort of potential energy because of its position in the gravitational field. The planets all have some potential energy from the sun, right? And roller coasters get potential energy from the Earth. So any celestial object, Earth, moon, star, galaxy, anything like that's going to have a pretty significant gravitational field, and anything in that field could potentially move. It has that potential energy, and if it's able to freely move, it will convert that potential energy into kinetic energy as objects get pulled together by gravity. So let's look at this roller coaster situation here. At the beginning, it gets pulled up by something, right? Gravity's not doing that. Gravity doesn't pull things uphill. So that's where the electricity company comes in, or maybe a gasoline motor generator, something like that. You've got some form of other energy is giving it its first potential energy. So usually roller coasters are hooked up to a chain. That chain pulls them to the top of that first hill right here, and then gravity takes over. So electricity gives it its initial boost up to the top of the hill. Then it reaches the top where it has its maximum potential energy. Right here at the top, that's the spot where gravity can do the most work on this object. It's the furthest up. So gravity has all of this room to accelerate it. So that's the potential energy I'm talking about. Is at the top of that hill, gravity can accelerate that roller coaster all the way down. Then it does, right? Gravity does its thing and accelerates the roller coaster down, turning that potential energy into kinetic energy. Then it gets down to the bottom here where it has its maximum kinetic energy. That's its lowest point. So gravity has turned as much energy as possible into kinetic energy at that point. And then it goes back up the hill and turns some of that kinetic energy back into potential, right? So up here, it has more potential to move than it does down here. So because of that, it has to slow down a little as it goes uphill. So think of gravity as like the energy bank. When you go uphill, you're storing potential energy, and then you can make a withdrawal, release that energy to go down the hill and increase the speed. So in this real life scenario here, we got the baseball that was hit forward, right? So it has an X and a Y velocity. It was hit forward that way, but it's also obviously hit mostly upwards. So it pops up into the air, and let's look at this from an energy standpoint. So up here at the top, it has the most kinetic energy and most potential energy. I think I've made that mistake on all three attempts to record this. So it has the most potential energy, the least kinetic energy, because it's not moving in the Y direction. It's still moving forward a little bit, X, so it's not zero kinetic energy, but it's a turnaround point in the y direction. It goes from positive y to negative y. So right there at the top, it's 0y. So it has no y direction velocity. All it has is that small x direction velocity, and therefore that's its lowest kinetic energy point. However, gravity, since it's at the top here, gravity is doing, it has the opportunity to change that, right? So it's up here at the top, meaning gravity has the most room to work with. It can send it all the way back down to the bottom. So unless somebody catches it or something like that, it's going to do that. Gravity's going to do its thing and send it back down to the bottom. So where does it have the most kinetic energy? At the bottom here. So right when it comes off the bat, smack off the bat, that's where it has its top speed. And then also when it comes back down, right? So let's look at this from an energy perspective. As it goes up and up and up, gravity is stealing its energy and turning it into potential energy. Then as it goes back down, that potential energy is converted back into kinetic. So it's the same amount of energy both times. So therefore, both of these spots theoretically will have the same amount of energy. So that's what is going on in that scenario. Now, that, of course, is in the magical physics land with no air resistance, like when we were dropping things on the moon. In the real world, the beginning here would actually have a slightly higher speed than the end, because air resistance will have stolen some of our energy along the journey, but both of those spots will still have a much, much higher kinetic energy than the top. That's for sure, because at the top, gravity has stolen quite a bit of that kinetic energy. So make sure you get this information copied down, and let's keep rolling. Let's take a look at the math involved here with gravitational potential energy. So we understand the concept that it's energy stored in gravity as objects go up higher on a hill or a roller coaster or whatever. Gravity then has more energy to work with, more potential to push them back down. So we know height is involved because I already told you, as we go up a hill, we have more potential energy. So let's look at the other things involved. One is the mass of the object, right? If your sibling is playing a prank on you and drops something off the second floor onto you, a baseball would hurt a lot more than a ping pong ball, and it's due to the mass, that the baseball is carrying more energy with it due to its greater mass. And also gravity itself. Objects on Jupiter would have a greater potential energy than on Earth because Jupiter's gravitational field is stronger. So that's the 9.8 that we know and love already. So that is the formula. And let's take a look at that algebraically. mgh. M is mass of the object. G is the strength of gravity on Earth, 9.8. And h is the height above the bottom of the path. Bottom of the path being a very key point. So oftentimes that's the ground, but not always. And let me show you an example here. So there's a roller coaster at Elages. I think it's called the Sidewinder. Man, that's my worst drawing of the 3 attempts, but that's okay. You get the point. It starts off at the top here, and it goes down, then it goes around the loop, and then back up to the other side, and then it does the same thing backwards in reverse. So that roller coaster actually never fully reaches the ground. The ground is like here. Let's give it like blue supports. And it's got supports that hold it up off the ground, and that roller coaster never actually fully reaches the ground. So let's say that the top here, let's say that it starts here at the top at 20 meters high, 20 meters off the ground. And let's say that the lowest it gets, that looks about right, the lowest it gets is 5 meters off the ground. Whoa, that My mouse kind of went rogue there. 5 meters off the ground. So this purple highlighted part here, that part never gets used. Gravity does not have access to that part in order to accelerate the cart. So the height you would use, if I asked what's the potential energy at the top of the path there, you would use 15 meters for the height. You'd subtract out that 5 meters at the bottom that go unused in this situation. Now here's where physics is different than math. In math, you get an equation and you use it. Okay, tell me what GPE is if M is this and G is this and H is this. That's math. Physics is real life. So you have to look at the scenario. So if this is a basic roller coaster scenario where the roller coaster follows the path and gets to the other side and nice and safe, just like we planned, then it's working with 15 meters worth of potential energy there, because it only goes up and down through that 15 meters. Now say some poor guy at the start of the ride loses his sunglasses. So let's use like green for his sunglasses, and the sunglasses fall all the way to the bottom. In that scenario, 20 would be the height for the sunglasses GPE, because it did use that bottom 5 meters, right? The sunglasses didn't stop and hover 5 meters above the ground. The sunglasses fell all the way. So you have to look at the situation to know what your height is. Oftentimes, it will be the ground, like the sunglasses situation, or throwing something off a building. Oftentimes it won't be the ground, like our roller coaster here that doesn't go all the way to the ground. Or maybe a roller coaster could come underground and make a tunnel, in which case it would actually increase your height. Instead of subtract, you would add that on there because you're going all the way down to the ground plus some more. So you've got to look at your height and how far above the bottom of the path are you. That's the real key here. And that's one of the tricky parts of energy, is H isn't just your height, it's the height, it's the difference in height, basically. How much room does gravity have to work with? In the roller coaster situation, that would be 15. In the sunglasses falling off your face situation, that would be 20. So you got to look at the situation. And a drawing, you guys know me, a drawing is always, I think, useful when you're dealing with physics problems, so that way you can see the situation and your numbers start to make more sense. And then there's that note, just to make sure I didn't forget to say it, that G is 9.8. So here's an example problem. I'll go over the scenario and then I'll shut up for 10 seconds and let you guys think it through, and then pause it and you can try it out. So we've got roller coaster at point A, 30 meters above the ground. And there's a little hint for you. And it's on Earth, so gravity's 9.8, and it's got a mass of 200 kilograms. Sorry, ignore this. It doesn't weigh 200 kilograms. It has a mass of 200 kilograms. So we know M, we know G, we have an H of some variety. We got to do something to it though, and go ahead and plug it in and see what you get. And I'll check in with you in 10 seconds, so pause the video while you work. Okay, spoiler alert, pause the video now if you're not ready. There's our equation, and there's our numbers, and you see what we did to the H. It's 30 meters off the ground, yet only 10 meters above, or sorry, 20 meters above the low point, because that low point B there is 10 meters off the ground. So these bottom 10 meters here, they never get used. So we subtract them out because they're not part of this situation. So our final equation there is 200 times 9.8 times 20 meters. Our height in this case is 20 meters. And you get 39,200 joules. Joules is our unit for energy. It's a derived unit. It's what you get when you multiply all these units together. So we've got kilograms for mass, meters per second squared here, which is a form of acceleration, right? Meters per second squared. Gravity is an acceleration. and we multiply that by meters. So kilograms times meters per second squared, this part here, that's a mass times an acceleration, right? We have units for that. Mass times acceleration, what does that give us? That gives us a force, newtons. So those first two parts, the m times the g, gives us newtons, and then we multiply that by meters. So a joule is a Newton meter. That's another way to think of a joule. It's a Newton times a meter, mathematically. So another reason why it's important to have kilograms, meters, and seconds. Everything needs to be in kilograms, meters, and seconds. Otherwise, our units don't match up correctly. So a Newton meter, a kilogram meter per second squared times a meter, kilogram meter squared per second squared is what you would call that. All of those are different ways of saying joule, Joule. Okay, so basically the same situation here, but the cart is heavier. It's up to 314 kilograms. Still on Earth with 9.8. Now it's over at point C, over here, 25 meters above the ground, off the ground. And we want to know what's its GPE now. So it's reached the second side and it's going to start going backwards. What's the GPE in this situation? So I'll be quiet for 10 seconds. Please pause the video and calculate. Unpause once you've got an answer. Cool. So here comes the answer. Just like last time, there's our GPE equation for potential energy. We need to get the height above the bottom point. So the bottom point is still point B at 10. The point we're at is 25. So we're 15 meters above point B. And we plug that into our calculator, 46,158 joules. So why is point B, what's so special about that? So let's think about what would the GPE be at point B, where there is, it is the bottom point. So what do we subtract? Would we do 10 minus 10? Yes, indeed we would. So this point here is the bottom point. So you can think if our roller coaster was sitting right here at point B, then it would be the bottom, right? Gravity can't do anything to that roller coaster. It can't push it left because that's uphill. It can't push it right because that's uphill. So it has zero potential energy from gravity there at point B, even though it's off the ground. Now your sunglasses would have 10 meters worth of potential energy because your sunglasses can still fall more. But that roller coaster cart, it can't fall anymore. It's at the bottom. It's got zero potential energy at point B. So yes, indeed, can you be above the ground with zero potential energy? Sure, if that's what the situation dictates. The sunglasses situation, that's not the case because the sunglasses can very easily still fall down. But the roller coaster, that's not going to go down because of gravity any further than point B at 10 meters. Let's go ahead and take a look at kinetic energy now. So kinetic energy is energy of motion. Anytime something's in motion, it's got some kinetic energy. So it's really as simple as that, whether it's a ball being tossed off a cliff or a biker going up and down a hill, it's got some kinetic energy anytime something's moving. So it's about as simple as that. But why don't we kind of look at some examples and dig a little deeper. So mathematically speaking, kinetic energy is equal to 1/2 times the mass of the object times the speed of that object squared, or velocity. When you square something, it loses direction. So it's just a number at that point. So kinetic energy is not a vector, and neither really is potential energy. Energy is just an amount. It's in a number. It doesn't have a direction associated with it. So algebraically, that's 1/2 mv squared, and I don't really like that. Let's call it KE. Sometimes it's called K, but I prefer the KE. I don't know why. So 1/2 mv squared, and when you do that on a calculator, do the v squared first. That way, you make sure order of operations are followed. So sometimes it might accidentally square your whole thing if you do the 1/2 times m times v squared. It might do 1/2 times m times v and then square the whole thing. Calculators are funny like that. So start with the v squared, then multiply by m, and then you can divide that whole thing by 2 or multiply by 1/2. Same thing. And again, kinetic energy is always positive. It doesn't make any sense to say negative kinetic energy because it just, the slowest something can be moving is not moving, 0. If it's moving, it doesn't matter what direction, it's got some kinetic energy, a positive value. So let's look at this example with the volleyball player. The volleyball has a mass of 2.1 kilograms. It's a little higher, a little below 5 pounds, like 4.5 pounds-ish, give or take. So volleyballs are pretty heavy, actually. It takes some strength to get those things moving. And it's got a speed of 30 meters per second. What's its kinetic energy? So I'll give you guys 10 seconds worth of video to pause and work that out, and then press play when you're done. Okay, so make sure you've paused if you don't have an answer yet, but we're going to solve it. So kinetic energy equation is equal to 1/2 times m times v squared. Sorry, my mouse handwriting is rough, but you get the picture. 1/2 times mv squared, which equals 1/2 times 2.1 times 30 squared and I made sure our units are good, so we have kilograms, we have meters, we have seconds, so that's what we want. Oops, don't forget to square your velocity. 1/2 times 2.1 times 30 squared, and when you plug that into the calculator here, let's do that. 2.1 times 30 squared, 945. So this volleyball has been served with a kinetic energy of 945 joules. So the math is really that simple. You just plug in the numbers and solve for what you need. The tricks here were like the height for the potential energy and making sure you square your velocity first for kinetic energy. It's pretty straightforward, really. The faster something is going, the more kinetic energy it has. You can see that because velocity is squared, velocity is more heavily weighted than mass. So velocity does have a bigger impact on something's energy than the mass does because that velocity term is squared. So it makes it so that velocity has well, that's why they call it power. You may have heard exponents called power before. It's because velocity has more influence, more power over the situation than mass does, because mass has a power of 1, velocity has a power of 2. So an object's velocity does matter more when we're talking about kinetic energy than its mass does, but its mass definitely matters as well. So one more practice problem here. We're just going to do this one verbally because the numbers are so much easier. So we're just going to plug it into the equation, 1/2 mv squared, right? So v squared is 4, 2 times 2 is 4, and that's our velocity here. So v squared would be 4. Multiply that by m. 4 times 3 gets us 12, and then don't forget the 1/2. Got to cut that in half. So 12 divided by 2 is 6. 6 joules for our ball rolling down the hill. This is revisiting our energy problem, but in graph form. So you can see at the beginning, our roller coaster did not have much energy of any kind. As it goes up the hill, the engine, the chain, electricity, whatever it is building more potential energy to bring it uphill till it reaches the top at point C, and it has its maximum potential energy. That's the highest it can go. Gravity has a lot of room to work with there. Then it starts going down the hill. So what happens is, well, gravity is converting this energy into that energy. So it's sharing, right? It's got a certain amount of energy, and that energy is moving from one type to the other until you get to the bottom here, where as much potential energy as possible has now moved over into the kinetic realm. Now there's still some potential energy on this one. That's a terrible arrow, but that's okay. There's still some potential energy here because you can see there's some parts down below. So that's not the lowest point on the whole track. So it's still got a little potential energy to work with, but for the most part, it's not, the situation won't be, you know, how am I trying to present this? Essentially at that point E, speed is carrying most of the energy, not gravity. That's basically what that means. So you can see how these two quantities go together, how as we go through the roller coaster track, potential energy increases when we're higher up, speed and kinetic energy increases when we're lower. So roller coasters are always going faster down here than they are up here or up here. And that makes sense, right? Because gravity's pulling them downhill. We've all experienced that before, and it works exactly the way you think it would. Now that does change things if there's friction. If there's friction involved, then your energy won't be consistent throughout because friction is stealing it. So let's say in this example here, in this picture, we've got a chemistry book and a physics book, and they're rubbing together. And it zooms in so we can see the molecules. So these yellow dots are chemistry book molecules, and these green dots are physics book molecules. And you can see it's not perfectly flat. We've got these little bumps and ridges and things. So when these two objects rub together, those bumps and ridges rub together and they catch and slide, and the molecules bounce into each other and they start to vibrate around, right? So this molecule could be bouncing that way, and this molecule could start bouncing that way, and so forth. So these molecules, as they rub together, you can feel it with your hands. I'm going to do that next to the microphone here. And if you rub your hands together like that, you can feel them start to heat up, and that's called thermal energy. Thermal means heat, like temperature. So that's kind of how friction, not kind of, that's exactly how friction steals energy from something like a roller coaster. So let's say this yellow portion here is the roller coaster car. And let's say the green portion is the track. Then what's happening is as the car rolls along the track, the molecules on the surface of the tire, of the wheel, are bumping into and rubbing against the molecules on the surface of the track, and that's causing some vibrations, some heat to be created. And that heat can't just magically come out from nowhere. So where does the energy for that heat come from? It comes from the kinetic energy of the car. So some of that kinetic energy gets taken and transformed into that thermal kinetic energy, where those, instead of the car as a big large object all moving down the track together, instead that energy is now being used to shake and vibrate these molecules as they bump into each other. So that's how friction steals energy from moving objects, is when you zoom in on the molecules, those molecules on the surface are kind of bumping into each other, rubbing against each other, and creating heat. And that heat is what steals the energy from our objects. So conservation of energy still works. The universe hasn't lost any energy or gained any energy here. It's just taken our energy from gravity and from motion, and it's translated it into heat. And that's what friction does. So you can see this example here, which I don't know if we're going to get to do our friction lab next week. If we do, it'll be like all you have to do is the conclusion part. Certainly, I'm not going to make you write a lab report next week. Maybe just like a 1-paragraph conclusion about some lab data might be the thing. But if we do, it will be exactly like this. We'll have a ball start at the top of a hill and roll down the hill. And we'll calculate its potential energy at the start of the hill, and we'll get its speed and use that to calculate the kinetic energy at the bottom of the hill to see how much of that energy was lost. So in this case, this child had 1,000 joules at the top of the slide and had 900 joules at the end of the slide. Where did that 100 joules go? Right? It's lost 100 joules. 100 joules went into the friction and turned into heat. So the slide and his pants or whatever would have heated up slightly from this trip down the slide. Honestly, 100 joules is a lot. It probably was more like 10 joules, but still, um, it was stolen from friction. That's where this energy went. And some slides are actually really terrible. You may have even noticed that sometimes you sit on a slide and like you don't even go anywhere because there's so much friction. So I guess it is reasonable. There's probably slides out there that might steal upwards of 10% of your energy, and those might be the types of slides that give you a friction burn, right? Like a rug burn or something like that, because you've literally been burned by this thermal energy that's been created by friction. It's not just a metaphor, it's a literal burn when you get a friction burn. So hopefully that's never happened to you, but some of you may know exactly what I'm talking about, like especially if you've slid on a carpet the wrong way, you get that carpet burn. That's from a huge amount of friction in a short period of time, and it delivered a quick burst of thermal energy to your skin, which caused a burn, just like any other heat would cause burn. So a little bit of biology background there too, but it's all comes from physics. I think every other kind of science can be turned into physics if you try hard enough. So hopefully this was valuable. Please fill out your exit ticket to get your points for May 1st. And we've got a homework over the weekend in order to make sure I have time to get you through a little bit of torque before the end of the year, because that's what's going to really set you up best for college. That's why we're only spending a couple days on energy, is because energy is pretty straightforward, especially the math. I want to make sure you guys have some exposure to torque before going to college, and hopefully that puts you ahead of the other students who maybe haven't seen it before. Because I always thought torque was challenging, though apparently my torque unit is quite popular because most of my students in the past have said that was their favorite unit, even though when I took physics, I found it to be the most challenging. For whatever reason, my physics students, that doesn't seem to be the case, and hopefully that's true again this year. And so, yep, have a great weekend, and please let me know if I can help with anything. Make sure you get your take-home quiz done if you haven't already. That's much more important than some random energy homework. So focus on that quiz if you haven't finished it, and let me know if I can help.